Hello everyone and welcome to today's live broadcast. Particle counters must now be calibrated with ISO 21501-4. Do your instruments comply? Presented by Joe Gecsey, the Life Science Application Manager at Beckman Coulter Life Sciences PCC, Particle Counting and Characterization. We are excited to bring you this educational web seminar presented by LabRoots and sponsored by Beckman Coulter Life Sciences. Beckman Coulter serves customers in two segments, diagnostics and life sciences. The company develops, manufactures, and markets products that simplify, automate, and innovate complex biomedical testing. More than 275,000 Beckman Coulter systems operate in both diagnostics and life science laboratories on 7 continents. Scientists use Beckman Coulter's life science research instruments to study complex biological problems, including causes of disease and potential new therapies or drugs. To learn more about Beckman Coulter Life Sciences, please visit www.beckmancoulter.com. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want, anytime you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window and type your question into the box that appears on your screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice that you will be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located in the lower right. And finally, if you have trouble seeing or hearing the presentation, please click on the support button at the top right of the presentation window. Or you can use the Q&A button to let us know that you're having a problem. Thank you. Now I'd like to introduce Joe Gecsey. Joe has been involved with the particle counting industry since 1984. First joining Met1 as an electronic design engineer, Joe has been involved in both airborne and liquid particle counter design, as well as multi-sensor systems for facility monitoring systems. He has also been involved in various standards involving particle counting in air and liquid. Joe is part of the TC209WG1 revision group on the main global cleanroom certification standard, ISO 14644-1 and 2, one of the 2 Americans on the committee. He's also involved with the ISO TC24/SC4 committees related to use and calibrations of various particle counting and characterization instruments. In recent years, Joe has presented information seminars in Asia, Europe, and South America on particle counting and numerous associated topics. Please join me in welcoming Joe. I will now turn the presentation over to him.
Thank you, Judy. Good morning, and thank you for joining us. And we'd like to follow today's talk with questions. I'm sure that people have various concerns, questions about both the ISO 21501 as well as the 14644. So happy to be able to speak about that and address that, all those concerns, hopefully get all the questions answered at the end. So again, I've been involved with some of the various standards, and there's always questions as new standards are brought forward. And none of them are ever quite perfect, but certainly they have an effect on us, and it's good to be able to have the chance to have dialogue about it. So briefly, today's agenda is to look at the history of 14644 as a starting document, just briefly, and then to look at the differences in the way these documents are applied to address both the issues of cleanroom classification as well as a more perhaps daily or weekly task of monitoring. Follow that with a review of the recent changes in the 14644 document that occurred in this last year, was effective in December, and to look at the demands that relate to 21501-4 calibration for airborne counters, not to go into it in great detail, but to kind of address that and to understand the impact or effect of that, to look at the benefits, and of course at the end to be able to have some further dialogue in that. So the main items to consider, realize is that 14644 now does reference this ISO 21501-4 method, which has been around for a number of years. Actually, it goes back to 2007. So it itself is not new. It's just the interconnection between 14644 and the 21501 calibration. Not all counters were originally designed to meet 21501, although most of the ones made in the last 5 years or so would. And also to realize that due to damage or misuse or age, particle counters, even if they were originally designed and produced to meet the standard, may not stay within the boundaries of the calibration standard limits throughout their lifetime. So it's a life cycle process for that. And to realize that 21501 itself is also being reviewed and looked at. Don't expect major changes, but that also will be forthcoming in the next 1 to 2 years. So the main thing now is just to realize that 21501 has its impact. If you're in a regulated industry, it might be important then to verify that your current equipment does meet that, and or make plans by budgeting and so forth to bring your equipment up to that level if it's needed. So just a little background on 14644. I expect most of the people listening in are probably familiar with it, but just to touch on it, started back before 1999. Previous to that, most nations had some form of a clean room standard, but that made it, of course, difficult to communicate internationally about various needs that might be required for a given corporation or application. So in 1999, the ISO 14644 document was put forward, and we're focusing in this discussion just on the first 2 segments of it, which deal with the cleanliness of air related to particles. Clean rooms can mean many things to people in terms of their needs. Certainly particles have been the predominant concern, but there are certainly some industries that are focused on various kinds of chemicals in the air, chemicals on surfaces, and so forth. Today, though, we're just focusing on these 2 segments that speak to the cleanliness in terms of particles in the air. One thing it's important to realize about ISO 14644 is that it really is addressing all industries. It does not think about the actual application or use. So we're looking at a document here that isn't focused, for example, on GMPs, or isn't focused on aerospace, or isn't focused on semiconductor. It just speaks to the needs of someone who has a very clean space at different levels, and a method to allow them to assess that on a consistent basis. So as most standards are designed, basically you put forward a method, you talk about perhaps tools or instruments needed to execute the method, and the intent then is that anyone can follow that procedure, use the correct instruments or tools, and come up with the same final analysis, the whole concept, if you would say, behind any standard. But again, this is something that applies to all industries, not specifically to any one. As I mentioned, ISO 14644 today consists of many parts, up to 15 of them at the moment, and that speaks to cleanliness in various forms. Again, we're focused just on the first 2 sections related to particles in the air. One of the things that is often very confusing, and it's important to realize a distinction, is that the instruments that are used for monitoring airborne particulate are really used in 2 different ways, 2 different intentions, even though you're using the same box, the same instrument. It really follows the need to look both at the formal classification effort as well as the more frequent, perhaps daily or even continuous monitoring to assure that the room stays not in compliance with the standard, but rather up to the level of quality needed for a particular procedure or process. So these are 2 different approaches, and people often confuse and apply the classification document to monitoring, or occasionally vice versa. But it's important to realize you do have 2 different needs addressed by this type of instrument. So when we look at that, if we look at the classification effort, for example, to start, it's something that's a formal study. It's done every 6 months or perhaps once a year. The number of positions, sample volume, and format, so forth, are all dictated within the standard. And there's a single ultimate pass-fail limit for the classification. You either have an ISO 5 at 0.5 microns or you don't, based on a limit for that particular size and that particular classification. One of the important things to realize in this called philosophical distinction between classification and monitoring is the assumption in classification that the room or zone is reasonably consistent in terms of particle concentration, that it's reasonably homogeneous. Anywhere you go, you get more or less the same reading, not exactly by any means, but reasonably close anywhere you go. So it's assuming somewhat uniform distribution. When we contrast that to the task of monitoring, you see something that's much more frequent. You're really trying to assess my day-to-day or week-to-week appropriate level that's in that zone or room. There are no formulas related to monitoring. You don't have a statistical methodology that relates to that. And often you end up with two different limits. You have alert and action in some industries, looking for maybe some general consistency or trending information, or perhaps even control in very high-risk operations. So the reports end up then in some quick form for understanding, maybe a quick control chart, some kind of a method that allows you to very rapidly assess the appropriateness for your task. And monitoring really looks at each position uniquely. You might have two positions in the same general classification of a room, an ISO 5 room as an example, that have unique alert and action values due to the type of process or the sense of risk associated with that particular position. So that's one of the key differences, is that in monitoring, we're looking at each point as a unique entity. So again, back to those sense of differences, the focus of assessment and classification is the room or the zone. And for monitoring, we're really making sure each point stands on the merits needed for the performance of a task or a particular procedure. So let's focus first on this task of classification, which is what the 14644 document points to. And its fundamental purposes, you could say, are twofold, really. One is that it gives us a common language. We can talk about an ISO class 5 or an ISO class 2 or an ISO class 7 room. Pretty much around the world, people have an understanding what level of type of room that is, what type of garments will be needed to maintain that room. So it gives us a common language. It's the first point. The second is it gives us a method, a statistical method, to evaluate that room and assess its readiness to carry out whatever task we've done. Again, we aren't specific to an industry in this document, so you might be putting a satellite together in a very large, high room. You might be putting drugs into vials or ampules. You might be doing surgery. This document doesn't think about that. It just says, here's a way to assess it without taking 100% of the air out of the room. And that's where the statistical method comes in. We don't know with 100% certainty what the room classification is at that moment in time. So if we're going to take a sampling of it, then the question arises, well, how many places and how much air at each point? So that's really the fundamental purpose underlying the standard, giving a consistent statistical method everyone could apply and evaluate an area and say, is it appropriate for the task I have planned for that room? In the standard, there are 9 different classes of rooms, ISO 1 through ISO 9, going from very clean at ISO 1 to not very clean at all in ISO 9. Most operations tend to be in the range from 5 to 8. But not always. Depends on the particular type of industry and method. Certainly, semiconductor industry utilizes ISO 2 and even ISO 1 at times. Very demanding, but needed for that particular type of operation to have success, to have high yield in the case of the semiconductor operations. It also outlines 6 different sizes to be used for the evaluation. So at the top here we have a listing of these sizes, 6 sizes, any one of which or several of could be used to classify depending on the process at hand. So these sizes can be used as needed for describing a certain process. So that standard has been in existence and been used by most industries since the 1999 initial release. Finally, after a number of years, in December of 2015, some revisions were put forward and published, so the document is now a 2015 document. So what changed? Well, in a sense, not a tremendous amount. It's important with most standards not to make radical differences unless for some reason the methods or technologies have shifted substantially. So you wouldn't say that it made big differences, but it did make a few. And I wanted to just briefly touch on those as we discuss this and its relationship to 21501. So some things, as I said, change. There's really 2 major ones that I'll address shortly to it. So the first thing is, the requirement that was there originally to address the upper confidence limit statistical method when you are sampling very few positions, less than 10 positions, has been withdrawn in the 2015 edition. The frequencies of retesting used to be stated as 6 months if it was ISO 5 or cleaner, 12 months for ISO 6, 7, 8, 9. That's no longer specified by class. The labeling of the class, no, that didn't change. We still have ISO 1 through ISO 9. Calibration of equipment, there's a slight difference. Always there was a need to calibrate equipment. That was stated in 1999 version. Now it points to a specific method known as ISO 21501-4. The basic the statistical side of things and the sample volume and time didn't change. However, the minimum number of locations did. And so we'll address that. And again, this was to put the standard on a slightly better statistical footing where we could see at the end of the assessment data that gave us a 95% confidence that we met the room classification. So again, the limits for the ISO changed, as we'll see, and the general classifications still the same. That's the same. The basic need here for the sizes, nope, no change with that. What we do see, though, are a couple of changes in the outlying points of the table where we had very small numbers statistically and ran into issues in terms of the successful sampling of those and using a statistical limit based on an extremely small number. So let's focus on the 2 main items, the minimum number of locations and the calibration of equipment. These are really the ones that impact people most. So minimum number of locations, so let's look at that. Previously, it was a simple kind of mathematical calculation based on the area of the room or zone. It might be an isolator we're talking about, not a whole room, but a box, a laminar airflow bench. Whatever the zone of interest is, we would measure that and get a value in square meters, and then take the square root of that area. If it wasn't a whole number, we increased it slightly. So if we had, for example, a 20 square meter area, we take the square root of that and say, well, that's not exactly, it's between 4 and 5, so we bump up to 5, and that would define the minimum number of locations for calling that area by an ISO code. As we looked at that from the statistical side in the group, we finally determined that that really wasn't quite sufficient. It gave us maybe 80-odd% confidence, but really not the 95% that we really were trying to achieve. So with the help of some consultants in statistics, one from Denmark, one from Japan, another from the U.S. It was determined that we needed to increase that, and we really needed something more like a chart in order to carry out that improvement in the statistical reliability. So in the current document, there is this chart, and I realize in my presentation here it's quite a small numbers, but if you look at this, you can see to the left we have a column that references the square meters still, so we're still speaking about an area based in square meters. And for any particular point in the column, you look at your number and find out if it is exactly that. If it's not, if it's in between, then you take the next highest one. And from that, then we derive a minimum number of sample locations. So a little bit of the same process, just based on a chart. So if we look at the example that's highlighted, where we had 36 square meters previously, when we would use the earlier method of taking the square root, that would have yielded a minimum of 6. In today's chart, that value is now seen to be 9. So it's an increase, not substantial, it's not doubling, but it is an increase in almost all cases to some extent for the minimum number of positions. And again, this is based on the need to try to get to a 95% confidence value for the determination. So again, a statistical method, we want high confidence. That's set to target to a 95% confidence. The second major change, and really at the heart of today's conversation, is about the calibration method, the ISO 21501-4, one that people aren't as familiar with generally, and certainly has come to the fore in this overall commentary about the changes to the ISO 14644 document. And again, previously, the statement in the document, the 14644 document, said you need to have a calibrated particle counter to execute the method. That's great, but there were many different types of calibration methodologies globally, or even within a given country. You'd find different variations, and that led to a fair bit of inconsistency. Well, standard ideally should be very consistent. We should find the same results based on the method and the instruments used, so that it, in a sense, gives us reliable and consistent information as a standard. So the committee adopted the known and specific method, 21501-4, and again, this has been around since 2007. So it's new in 14644, but not a new method. So previously, most people did at least a basic calibration when they talked about calibrating the particle counters. They checked the size, they checked the false count rate, that is, could it zero count correctly if it had very clean air, check the flow rate, check the sample time, make sure that all that was known so that we can evaluate particle counts per volume, per cubic foot, in some cases per cubic meter more often today. So basic calibration gave us assurance that the instrument could carry out that task. What we did with 21501-4 is certainly those basic tasks, but also involving a couple of other further tests, counting efficiency in particular, that is used to evaluate the consistency of the instrument over its lifetime, as well as the reproducibility or difference between instruments that might be used for this method. So based and using that standard, we gain an improved accuracy of count, repeatability over the lifetime of the instrument. These instruments typically will last 7, 10, I've seen even 15-year use of these instruments. And we'd like to know over that lifetime that we're still getting reliable information from it. So it's helping us achieve that. It's helping us achieve better unit-to-unit reproducibility. So counter A and counter B give us fundamentally the same results as we sample in an air. One of the challenges always with particle counters in the open air is they never sample the same sample between two instruments. We can't pass in series a sample through instrument A and then the same exact sample through instrument B. So there's always that bit of challenge that the air that we sample is never precisely the same for the two, but we'd like the instruments, if we could force them to sample the same air concentrations, to really read the same, and That's part of the effort in this counting efficiency step of this method that is achieved. So we get better consistent performance throughout the lifetime, and it ties us into a single method pretty much globally for calibration, and whether or not you're in a regulated industry and using the GMP, the good manufacturing practice methods in life sciences and pharmaceutical or biopharma. It helps bring that consistency, again, to the document and to the daily use, so both in terms of classification and in monitoring. So also, I can mention briefly that 14644-2, the companion document, was also revised, and it's focused on monitoring. So -1 focuses on classification, -2 focused on monitoring. I'm going to touch on that very briefly here, just because, again, it does relate to our discussion today. And this is not, again, a prescriptive or formula-based document in -2. Monitoring occurs in 1,000 different ways in all the various industries, so it's impossible to really put together a standard that describes a method. However, what 14644-2 speaks to is the need to look at, in terms of monitoring, the various needs. We need to put together a plan, we need to approve it, we need to execute it. So all those are discussions that are made in this -2, speaking to continued performance of an area appropriate for the task, be it that you're doing surgery or assembling a satellite, even painting a car is done under fairly clean conditions. Not nearly as clean, though, as semiconductor might be or as pharmaceutical. But all these are various uses that could be seen, and we want to know day to day or week to week that we're still okay in terms of our cleanliness in particle concentration. So basically, this is focused on something a little different than classification. This is focused on giving us a continuing flow of data over time. Now, that might be a weekly or monthly basis. It might not be so frequent. It could be, though, second by second. But somehow it looks at this at an appropriate time interval, as opposed to classification, which is an event that happens once every 6 months or once a year, more commonly. So do we know each day or each week that we're still within the boundaries we seek for our process environment? And this is what monitoring does. In this framework, then, we look at the aspect of creating, executing, maintaining a plan, and that's pretty familiar to most people working in the pharmaceutical, biopharma environment. And we do see, though, an interesting reference or increased reference to risk in this document for any industry. So we're talking about, do we understand if we don't monitor or monitor less frequently, do we open ourselves to greater risk for our particular process? So it has some discussion of that as well as looking at the methods to analyze the data. So fundamentally, one of the important parts, as I mentioned in this discussion of risk, is that some industries are more focused on that than others, but again, being an industry-neutral environment in the ISO document, we're not looking at a given industry, but always whatever you're doing, you see a certain level of risk. You say, well, I'm painting my car, or I'm doing a surgery, and I'm trying to do it in a specific type of environment or room. If I lose control of that, what is my risk for failing in my particular process? And in this document, though, we do mention that, yes, there could be some regulatory agencies that have different methods. So we'll touch briefly as we finish this talk about the GMP documents, the Annex 1 and so forth, that many people in the biopharmaceutical industries need to address. So it says there might be some other things that even supersede this. There's a general discussion of monitoring and things to consider, think about, and plan for, but there may be other methods and controls depending on your type of industry. There's some various counsel in here thinking about the things that can affect particle counts in a room, the airflow, the number of people, and so forth. There is also the council that consider to go back and review a plan. So there should be some kind of a review on a periodic basis, maybe once a year, maybe every 2 years, to look at the plan that you've put forward and assess, is it still appropriate? Do I need more? Do I have more people in the room and I need to change my limits? Do I have fewer people? Have I added a new process? Those things should be considered in monitoring. It shouldn't be a fixed document that was issued 10 years ago and has never been looked at again or changed, because in many cases processes and technologies change, and we need to assess that on occasion. Maybe the limits were set too high. Maybe there weren't enough places done at the time. Whatever it might be, it should be reviewed. It should be a living document. Again, in 14644-2 as well as in 14644-1, there is a reference as monitoring that airborne particle counters should be calibrated following ISO 21501-4. So that reference shows up in both these documents, both the one for classification -1 and this document for monitoring -2. I wanted to call attention to those who might not be so familiar with the warning levels and settings to an annex that is, as they say, informative, which means it's guidance, it's counsel, it's not mandatory by any means. But to realize that when you deal with pressure differential as well as airborne particle counts, often you need to think about your warning limits in a different way, because both for pressure differential and for airborne particle counts, you have instances where there's elevated or notable changes, but yet it's part of the normal activity. For example, in pressure differential, when you open a door in a room, the pressure is definitely going to change, be it a positive or negative one, for the short term that the door is open, and then ideally it returns back to the previous level. And you don't want an alarm to occur. You know, it's a significant change in pressure. Same might be true when you consider airborne particle counts in a certain region. An activity might increase the particle count level momentarily, but it's part of the normal process. So it's important as you think about a monitoring plan and try to establish any form of warning levels, whether you call them alert, inaction, or anything different, to make sure it references what is normal for a process. It means you really need to spend time understanding the process in order to set these limits, because particle counts and pressure differential really are a different style of data set, you could say, compared to, for example, temperature or humidity in most rooms. Those are pretty steady, and you could say that they have an average value plus or minus a small amount, plus or minus 5% or something like that. Particle counts and pressure differential have more radical changes. So as you set alert and alarm levels, you need to think about that reality of that particular type of data that you're working with. How does it relate to Annex 1, commonly used in biopharmaceutical, and both the European and the more global PICS documents have an Annex 1 that ties to the high-risk production of sterile medicines. And how does this change in 14644-1 affect that? Well, in changing 14644-1 and -2, we didn't change the GMP document. They're totally distinct and separate entities. But ISO 14644-1 is referenced in the annex as a document that sets forward the number of positions and other aspects of verifying that a room, which in that document would be called then grade A or grade B, grade C, grade D, not ISO, but a grade designation, would still be classified and be monitored in an appropriate way. So it ties these two documents together in that way. So again, back to it, as we mentioned before, minimum number of sample locations has increased, and it uses this chart. So when you're thinking about how many positions do I need to classify my grade A zone, this then has the impact of increasing, in most cases, the number of positions which you must monitor to verify and say, yes, I have a grade A zone. You're not calling it ISO, you're calling it grade A, and that means something different. And that's fine. You don't have to have a room always classified by ISO. That's again, it's industry neutral, whereas something like Annex 1 is very specific to an industry and a process. But it points back to this. So, for example, again, if you had that 36 meter square room, previously you would do 6 positions for your classification effort to call it grade A. Now you need to do 9 positions. The specific calibration method then is also triggered by that reference to the 14644-1 and -2. So when we look at this overall in terms of these changes for 14644, they did take effect in late 2015. For most areas, additional sampling points will be required. That means, and sometimes then additional cost in terms of sampling and recording and analyzing the data, but you end up with better data, you end up with higher confidence the room perform as needed. Some of the new instrument designs can help mitigate that impact of extra sample points needed, extra time needed in many industries. So we could look at that and say, well, can we do something with today's technology that helps us out? Just like our cell phones are much more practical and useful than the previous wire-connected phones in our lives. So in that same way, technology here can help us streamline workflows, make the organization of how you do the classification or monitoring much more consistent. There are software wizards in many cases to guide the classification effort and to make sure the proper number of positions are taken. And we also have higher flow rates available now so that this amount of sampling, for example, for grade A, where you need to take a full cubic meter, can be reduced to 20 minutes or 10 minutes rather than 35 minutes. So there's various things that can happen with improved instrumentation today. So again, if we take a moment and we look at the monitoring side of this and classification, these are really calling for 2 different documents. When we talk about classification, we talk about 14644-1, or we talk about Annex 1 if we're driven by the designation of grade A, B, C, D. When we monitor, it's really your own company's standard operating procedure that defines the monitoring process. There isn't a document that specifically sets forward formulas. That's in classification, true, but it's not in monitoring. And so, again, just realize that you don't want to take classification methodology for minimum number of points, for example, and apply it to monitoring. In most cases, monitoring involves really 1 or 2 critical points in an area or a zone, not 6 or 9. Just depends on the type of operation. So again, monitoring is a way to understand that your control of risk in your operation is appropriate, that you have enough information to say, I've tried to control my risk as well as possible regarding any particular contamination from particles or any effect in my process due to airborne particles. So just briefly on the particle counter, we look at this particular instrument and what it does, and this goes to the classification side of it now, getting to look at the 21501 document in particular. Basically, a particle counter uses bright light in a mode known as light scattering to detect particles. So we have a beam of light, today it's typically a laser diode, and we pass particles through that. As a particle gets into the beam, it scatters light. From that information, we understand A, an event occurred, and B, by the amount of light scattered, we have an idea of the size of the particle. And this happens very, very quickly, within actually milliseconds, as that particle moves through the beam. This information is passed forward, and so we count in real time. That's one of the advantages of this particular type of technology, is we have very quickly a picture of our environment in terms of particles in the air, and that it is or is not appropriate to the task at hand. Well, how do we know it's seeing particles of a certain size? How do we evaluate that? What form of tests and so forth do we use to both design and to use this type of instrument? Well, that's where the calibration document comes in, and again, 21501-4 as an international document gives us a good base to establish a method. And in order to calibrate these, we can't just grab air particles out of the air. Rather, we use very well-sized particles. These are usually PSL or polystyrene latex spheres that have been aerosolized, put out into the air. And even though they're very, very tightly controlled, they do have some deviation, standard deviation about it. They're almost perfect, but not absolutely perfect. So you find particles from JSR or from the American Thermoscientific Duke, what used to be Duke, commonly available, and these are concentrations of very, very precise but slightly variant particles, and the particle counter then samples these. They're aerosolized, introduced one size at a time in most cases, and we evolve a calibration curve or response of the instrument to known sizes of particles. So then we create this type of curve based on the information we have from each of the sizes we might use. For example, a 0.3, a 0.5, a size particle, a 1, a 5. Often they're not exactly those sizes, but they're close. So we might then develop a curve based on that type of information, and we know then the performance of the instrument. And of course, what we want to do is not just know it at this moment. We'd like to, over its lifetime, know that it's still appropriate. So that's what 21501 calibration is about. And that helps us improve the consistency for various regulated industries, in particular the pharmaceutical, which again is the GMP, the Good Manufacturing Practice documents. So from Europe, for the FDA, PICS, they all look to this type of method, and they want to know with some assurance that these instruments do perform correctly. And so you'll often find regulators asking for calibration documents, and now they're going to expect that those would meet or show a reference to 21501-4. Not instantly. I think regulators, even though they are very demanding, realize that it takes an industry some time to come into accordance with changes in the standards. So they're expecting this, and they expect if you don't have currently satisfactory performance of the instruments, that you have a plan in place to get there at some reasonable point in time. Next year, maybe it's a matter of budget, of course, for a lot of instrumentation. Next year, you've got this plan in place to get the instruments upgraded so that they will meet the calibration standards. So again, we look at the old methods or even commonly simple methods of calibration compared to 21501, and we see that there's more tests involved, either in the design, in the production, or in the use at the end user site, that they meet these various aspects of it. And typically these calibrations are done once a year. However, in some industries, many of the life science, the biopharmaceutical industries, they look to do this every 6 months because, again, their sense of risk is different than other industries. You may have a high sense of risk, and you want to know your measuring instrument is always known to be in operation correctly through calibration. So what do we look for when we do this? Well, certainly we look to volume, because we are talking about particles per unit volume, per cubic meter, per cubic foot, whatever the measurement volume might be or referenced. We want to know that. And typically, most of these instruments operate in a time mode. So we know the flow, we verify that in the part of calibration, we know the time period, therefore we can speak to a given volume. We can say, yes, we know that we have a certain volume sampled, and therefore when we count particles, we can reference that volume and understand particles per volume. Resolution is another aspect. We want to know about particle sizes. We have particle restrictions. We say, oh, we want to know that we're within limits to have no more than, a certain number of particles per size or larger. These instruments are normally set up in what's known as cumulative mode. They talk about a size and larger. 0.5 micron and larger, 5 micron and larger, 0.1 micron and larger. So we want to know that they're correctly sized. So we go conduct a resolution test. And resolution is fundamentally telling us that one size level is not encroaching on another, that we can understand how well we can define particles that are a certain size in the air. And of course, in the beginning, we do this with test particles that are exactly a known size. That's helpful. But we have to realize that we're trying to make sure that that's correct. Counting efficiency is probably the major test that's changed or added for most people. And we're trying to control the biggest variability in the particle, in between two different particle counters. And we also want to know, of course, over its lifetime that it's consistently giving us good results. Counting efficiency can help. The test is a little bit more involved, and you have to have some kind of a reference standard instrument. So this can be done on site. Many companies have instrumentation calibrated on site, but it means that the technician brings more equipment in, takes a little longer to verify counting efficiency is within the limits under 21501-4. Well, what are those limits? When we talk about counting efficiency, what we're trying to do is understand that an exactly known level of particles going into the inlet shows up on the display or the report print or the electronic record, which you think would be, oh, okay, that's pretty straightforward. Particles in, particles reported. Well, the difficulty is always knowing exactly how many particles went in. So this is a challenge we have, and we accomplish this task then by having a reference counter to compare to. So we have a perfect reference, you could say, and we have a concentration that's evenly distributed between the perfect reference and the counter we want to test. So these two instruments are sampling exactly the same atmosphere of precise particles, and therefore we can kind of get a sense more correctly that we have concentration, counting efficiency in comparing the two instruments. So we start out with a traceable calibrated standard. We have a environment here represented by the blue tub that is a consistent concentration of a known size particle. We introduce that into the test, and we say, well, here we have, in this example, 0.5 micron particles, and this particular instrument is one that will give us a rating at 0.3. So we expect to see everything above 0.3 and larger and look at that concentration of particles. Okay, that's a good start. At least now we have a sense of what the number should be, in this case, this example, 2,000. And so based on that, then we say, well, now we want to compare the other unit to it. What do we do? So we start with this idea. We have a known concentration, and we put that into a particle counter who's got higher sensitivity than what that concentration is. So we start out, for example, 0.5 micron challenge, 0.3 micron setting. We should see everything that's there. Notice, though, that that curve is not a single spike. It's a it's generally a Gaussian or a curve that has a distribution to it, fairly tight if it's got good resolution, and but it is a distribution. It's not a absolute spike, you could say, at 0.5 microns, because there's variation both in the challenge material, in the perfect spheres that we send in. There's also some variation due to the instrument. By resolution, we know what that variation should be, and it's within limits. But when we actually take a challenge in, we'll get variability there. So then if we put two instruments and sample simultaneously this atmosphere that's well mixed, we then would see the 2,000 value in the first in the challenge, but we see a different number. We see a value of 1,000 in the unit we're testing. Why is that, and is that correct? Well, yes, it's correct because the counter is designated under 21501 to report 50% of the challenge at that particular threshold size of 0.5 micron where it's set, plus or minus 20%. That's the test. Why does that occur? Well, because the traceable standard shows a value of 100% because its threshold is set way down here at 0.3 micron as an example, whereas the threshold of the unit under test for 0.5 micron is set right in the middle of that curve. So if we look at a typical Gaussian curve and are looking at the peak of it, what we see is that threshold size and greater gives us 50%. And so again, that's the target of the test, 50% plus or minus 20% for that most sensitive size, a very lowest size a particular instrument is capable of sampling. That might be 0.1 micron, that might be 0.3, might be 0.5. Whatever it is, it will be set at what's known as the 50% point. However, in this method of ISO 21501-4, there's actually two tests related to counting efficiency. One is, if you send it in the particles that are right at the very most sensitive threshold, I see 50%. But what if I set it like we did the test one? What if we give it a little bit bigger particles, somewhere between 1.5 to 2 times the size, okay? And then say, well, here, I'm going to send in bigger particles. I'm going to keep my threshold still at 0.5 as an example. I'm going to send in 0.75 to 1 micron size particles, and will I see 100% of them? Well, that is the challenge and the designation there. We should be able to see, ideally, 100% plus or minus a small amount. In fact, plus or minus 10%. So counting efficiency under 21501 involves 2 steps. Size of particles that's right at the threshold, minimum threshold capability of the counter, and a size that's 1.5 to 2 times, and we should see 100% in that second test. One of the things about the current revision discussion is what tests are appropriate for various stages of a particle counter's life, in its design, in its production, in its lifetime of use. And those are different, and so this is a tentative discussion of what is appropriate to use in the field, and that statement of calibration, the test or the calibration over the lifetime, involves fewer tests done in that time period, what we would call generally the calibration time period, versus when, for example, a unit is first designed. It's much more exhaustively tested, as well as in the initial production use of it. But over the lifetime of the instrument, just a few of these tests are needed to verify that it is continuing to operate as designed. So this is one of the discussions that's coming up in 21501. So basically, as a summary, 21501 delivers better compliance, better accuracy of counts over the lifetime of the instrument, and improved correlation of counts over the between two different instruments. So again, just as a summary, realize that not all counters were designed to or continue to meet 21501-4 methods over their lifetime. Maybe sometimes they weren't designed correctly, or with this in mind, or perhaps they've been damaged or just aged over time. The light source, for example, the laser, has degraded over time, and therefore the counting efficiency test fails. Also realize that the counters, this method applies both to counters used for classification and for monitoring. ISO 21501-4 itself is under revision discussion too. I'm involved a bit with that, and I can say, again, it's not going to be a major radical change in the processes that are involved. It's just trying to make some improvements and consistencies in that method so that as it is used by various industries, it is practical and not too difficult a test to execute, not one that costs extraordinary amount of money to know that a given instrument, the particle counter, continues to operate in the way it should. So basically, the fundamental task for most people in looking at this requirement for 21501 is simply to confirm that your current instruments do meet the 21501, and if they don't, start the process of setting up replacements or getting to the point where you do meet the standard at a reasonable period of time within the next year or so. So with that, I'll say thank you again for your attention and interest, and turn it back to Judy for any commentary and questions.
Thank you, Joe, for that informative presentation. It's time for Q&A. If you have a question you'd like to ask Joe, please do so now. Just click on the green Q&A button at the lower left of the presentation window, type your question into the box that appears on your screen, and click on the send button. We'll answer as many of your questions as we have time for. Let's get started. Our first question is, do you know the typical pressure difference that has to exist to maintain positive pressure in a clean room?
Okay, inherent in that question, hidden in the question, right, is the statement that there's both negative and positive pressure rooms. Sometimes you use negative pressure for containment. If it's a positive pressure room, this will depend sometimes on the industry. For example, in GMP documents, they talk about a certain level of pressure for high risk or critical areas being maintained. And this can vary slightly between industries or between the types of work to be done. There is a lot of discussion about this in the industry right now because of the thinking about energy cost. It costs more to pressurize a room, so as you increase the pressure, you have more issues as you try to build that up. You certainly want to have a positive enough pressure to keep particles out. And that tends to be, 10 to 15 Pascal, something in that level is considered useful. But, the current technologies and concerns with energy probably are going to allow that to be a little bit lesser amount. But again, it depends on the risk. So I don't know that there is a universal differential pressure needed. In some cases right now, you're beholden to, let's say, a GMP document and kind of stuck with it, you might say. But just realize that there is discussion going on even amongst the ISO group within the industry looking at energy costs and trying to find a good level that helps satisfy the needs of the process, but also is not necessarily just simply based on historical levels that were set many, many years ago, and we're not necessarily concerned with energy cost.
In ISO 14644-1, note section, some particle counters cannot be calibrated to all of the required tests in ISO 21501-4. If this is the case, record the decision to use the counter in the test report. Does this mean that the use of ISO 21501 is not dictated for the calibration of, is it ISAPC?
It means it was a consideration, you might say, put in by the committee that changing all the particle counters used by a particular customer or one point, particular user or particular facility might be a onerous financial cost to do instantly. So again, not all counters were designed or are maintained to that. What it does mean, though, is you have to record that on the document for your classification. It'll show up as, I didn't use an ISO 21501-4 instrument. That's going to tend to be a flag to regulators in those industries that your instrument is not really up to perhaps snuff, up to what should be done, and therefore the results of the test are perhaps called into question, which generally with regulators is not a good idea. So, the direction here is trying to give a bit of leeway, you might say, in the first years of the implementation. But I know regulators are going to be looking at these requirements, and it's something where if you put that on the report, it's probably going to be called into question. So not a wise way.
I have a contract company come in and do my formal classification each year. So do I need to still have my particle counters calibrated to ISO 21501-4 when I'm only using them for monitoring?
Yes, you would. And again, this goes back to the -2 document and its reference to 21501-4 as involved in monitoring. And in some ways, you might almost say it's more important in reality, because you want to know that as you use that instrument to evaluate for your process day to day or week by week, that your area continues to meet that. And again, by using 21501-4, you have a very consistent method of looking at the health of the instrument each year or every 6 months. So you have higher assurance that the values you're getting for your area as you work day to day or week to week or month to month taking those samples do in fact meet your requirements for your process. So yes, it's in the document for monitoring, and regardless, it's probably good wisdom.
I would like to once again thank Joe Gecsey for his presentation. Do you have any final comments?
I think certainly to say that in the ISO world, we constantly look at evaluating these standards. We try to make them appropriate for the industry or industries that are involved. We look for suggestions, information, commentary, of course, as we draft these. Ideally, each document gets reviewed every 5 years for changes in technology or if it's still appropriate or what might be needed. So for those who are using the documents, we appreciate always input to concerns, challenges, technologies that might dictate better methods. So I just encourage people to work with the people in their country or company who are involved with standards and make recommendations when they see fit. So that's certainly input appreciated. Last comment would just be that although these changes are notable, you might say, they're not, shouldn't be highly significant. There might be a few more points needed to satisfy 14644 or a grade A, B, C, D designation. But the purpose, again, is to build confidence that that zone or area meets the requirement needed for that particular aspect, and the risk is controlled well enough. So there's a purpose behind it, and hopefully we've captured that well enough in the documents. So with that, I will say thank you for everyone's attention today.
Well, thank you once again. I would also like to thank our sponsor, Beckman Coulter Life Sciences, for making today's educational webcast possible. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through January 13th, 2017. You'll receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now. Thank you for joining us. We hope to see you again soon. Bye.